With this lesson, we're going to be writing the equations of rational functions from a graph. We've already focused on some of these key features graphically and algebraically. Now we're going to create that actual equation based off of some of those same properties. So looking at this first graph here, one of the first things I notice is a vertical asymptote. This vertical asymptote is when x is 2. If we go back to the equation of a rational function, the vertical asymptotes came from that denominator for whenever the denominator was 0. If the asymptote is at 2, then we would have a factor of x minus 2 in the denominator. Another key feature I see is the x-intercept. Our x-intercept is at 4. The x-intercept happened when the numerator of a function was 0. And this is because, I'll just write this down here, algebraically, we would set this equation equal to 0 and solve, and I multiply that denominator over. 0 times anything is 0, so I'm just worried about when that numerator equals 0. In our case, that numerator is equal to 0 when x is 4, which creates a factor of x minus 4 in the numerator. There are not a lot of other key features here, but some that we can check is this horizontal asymptote. The horizontal asymptote is at 1. This would happen when we think about the degrees. So right now we have degree 1 over degree 1. That's the same degree on top and bottom. When we had the same degree on top and bottom, we would use the leading coefficients. In our case, 1x and 1x is the current leading coefficients. But that does provide me a y equals 1 horizontal asymptote. Another thing I can check is this y-intercept. So the y-intercept is at 0, 2. That means when x is 0, that the y would be 2. And let's just check out what we have. Negative 4 on top divided by negative 2. Negative 4 divided by negative 2 is 2. So yes, that y-intercept does check out. So our equation that we are left with is just the x minus 4 over x minus 2. I'm going to come back to this example in just a second, but this is the equation we need. So we go to the second one, and we have a little bit more complicated graph. We have more features going on, like this vertical asymptote. This vertical asymptote is at positive 1. We have another vertical asymptote at negative 2. Just from those two pieces, we know we would have a factor of x minus 1 and x plus 2 in the denominator. The denominator showed when we would divide by 0, creating that undefined value, which is this vertical asymptote. We also have a hole. All right, that hole is at positive 2. A hole occurs when there's a common factor in the numerator and denominator. So that common factor of x minus 2 would make this hole happen when x is 2. We don't know the y value. We would have to plug in x to get this y value, but we don't have to check that right now. We just know that x minus 2 over x minus 2 creates this hole happening when x is 2. There's also an x-intercept at negative 1. So I know it would have an x plus 1 factor in the numerator. Remember, the numerator shows you the x-intercepts because that's when the fraction would equal 0. This hole is already going to cancel out. It would disappear when we reduce the function. So x plus 1 is the only other factor in the numerator that would make this x-intercept. There are no other x-intercepts. There is a horizontal asymptote occurring at 0. For that to happen, the degree of the numerator needs to be smaller than the degree of the denominator. y equals 0 occurred when we had a smaller degree on top than on bottom, and that is the current situation right now. So it looks like we might be finished, except there is an issue. All right, one thing we didn't talk about in the first one, and that's why I'm going to go back to it, is that I could have a constant factor outside. If that constant factor A was something like 7 or -4 or 3/2, that value would just vertically stretch or shrink this function. It would not change the degree of the numerator. The only way that we would change the degree of the numerator is if we had another factor of x in the numerator. We don't. We just have these two factors in the numerator so far. So let's test out what could this vertical stretch be by plugging in another point. And one other point we could use is the y-intercept. So if I use that y-intercept, that's an xy coordinate. That means that y is -1 when our x value is 0. So I'm going to plug in all the x's, or plug in 0 to all the x's. As I'm plugging this in, I realize I don't actually need this whole. I can go ahead and reduce that, but it's not going to hurt me to use the whole either. All right, so I get 1a on top. 1 times a is just 1a. And in the denominator, we have -1 times 2, so -2. Solving this equation, I'd multiply -2 over and get +2, so a is 2. That means that when I'm working out the actual equation of the function, I would have a 2 x plus 1 x minus 2 over an x minus 1, an x plus 2, and an x minus 2. We can see we have a hole in the graph. We have a vertical asymptote at +1 and -2. We have an x-intercept at -1, and there is some type of vertical stretch going on. We would just need to see that by checking another point.